Yesterday we gave you an introduction to cosmology, and Anjan started to give the theoretical basis for cosmology, which is important for what we'll discuss now. And now we'll start the lectures on weak gravitational lensing. Before that, in order to motivate weak gravitational lensing, I will review quickly some of the things I discussed yesterday. And then I'll just remind you that we now have established this standard cosmological model that we call lambda CDM. So the lambda stands for dark energy, which composes about 70% of the energy density today. CDM stands for cold dark matter, which is about 24% or so. And in this model, there's also, of course, the standard model particles, which are partially baryons, and also radiation photons, such as photons, neutrinos, and so on. As part of the model, there's also an inflation phase that gives us the initial condition for the formation of structures. And of course, underlying to all this is Einstein's theory of general relativity to give us the force of gravity, which is viewed not as a force, actually, but as a curvature of space-time. All right. Now, as we saw, there's different ways of probing the universe in order to understand these components better. All of these components, dark energy, dark matter, inflation, and potential modification of gravity, pose some of the most pressing questions in fundamental physics today. So the question is, how can we go forward, make more precise measurements, and try to shed light on one or several of these questions, hopefully. So as I said, there's two classes, two handles that we have on cosmology, roughly speaking. One is the geometry of the universe, so that's the measurement of the expansion history of the universe when it's smooth on large scale. So this is the background expansion without looking at the perturbations around this background. And we saw that there's different probes to do this, such as supernovae, baryon acoustic oscillation, and other effects. For some reasons, some of my lines have disappeared, which is a bit strange. And then there's also another class, another handle, which is the way structures grow in the universe. And because the growth of structure depends on the expansion history, as well as on gravity and actually also on thermodynamics, then the way the structures form and their nature and their properties depend on the components of the universe, and therefore give us some very important information on these dark ingredients in the universe. Okay, and all of the cosmological probes that we discussed, which yesterday I reviewed, give us information on one of these aspects, or sometimes a combination of these aspects. For instance, supernovae gave us a geometrical measure, but for instance, structure from galaxy surveys can give us a combination of both structure growth and geometry. And gravitational lensing, in particular, is one of those. We get information both on the geometry and on the growth of structure. Okay. Yeah.
When we study large scale structures, sometimes I see people talking about even the effect of cosmological expansion on their size.
On
the size of the structures. Do they respond to that mention? The largest structures will.
Yeah. Yes. Well, I mean the statistical properties. So the size. Once they've collapsed, they're not very sensitive to. They're not sensitive to expansion anymore. But the statistical properties, so the number of collapsed objects, their number as a function of mass, the property of the filamentary structures, and so on. So all the non-Gaussian statistics of the density field depends on the expansion, because basically the formation of structures, as I was trying to illustrate here, is a competition between gravity and expansion, right? So gravity wants to make the structure collapse, while the expansion wants to blow them apart. So if you have more expansion, it tends to slow down the formation of structures. So for instance, if you have a model where you add the dark energy component, which is a late time acceleration of the expansion, then you tend to freeze the formation of structures, or at least slow it down, right? So that's why the amount of structures as well as their detailed statistical property depend on the expansion, which as a result depend on things that affect only the expansion, at least mostly the expansion, which is like dark energy, for instance. It also, of course, depends on the property of dark matter, because dark matter dominates the dynamics of the structure formation. And so if you change the property of dark matter, you may also affect the structures. So that's why it's more complicated to interpret than just geometrical probe, where you just measure basically, let's say, the angular diameter distance or the Hubble parameter as a function of time. But there's a lot of information on the ingredients of the universe there, and also on the expansion as well. Just a different way of probing. Of course, this is also sensitive on the initial condition, like we discussed yesterday, the initial conditions of the initial seeds of the structures, while this is not, because this is only looking at the background expansion. So this is more complicated, but also more rich. All right, so we saw these different probes, so the cosmic microwave background, the gravitational lensing, galaxy clustering and clusters, and supernovae. As I said, they give us a combination of measurement on the geometry and also on the structure formation. And what we'll focus on from now on, at least I will focus on, and Jan will continue telling more about the processes, physical processes of structure formation, which we need as well, is on gravitational lensing. So gravitational lensing is illustrated in this diagram. I'll give you a much more detailed description in a second, but it's basically the bending of light predicted by Einstein's theory of general relativity when the photons traveling from a distant object pass through density inhomogeneities. Right? So in Einstein's theory of general relativity, gravity is not thought as a force at a distance like we used to think in Newtonian gravity. It has the remarkable change of paradigm that gravity is a phenomena which is actually reflects the curvature of space-time, and basically the curvature of space-time affects not only massive particles but also photons as well. And so by looking at the effect that this lensing effect, or this bent trajectory of photons, has on the observed shapes and position of objects, then we can learn about the distribution of mass in the universe. And because the distribution of mass is more directly related to theory and also to the properties of dark matter, then we can learn directly more detailed, more precise information on these two aspects. Now, gravitational lensing has a special place in astrophysics because of this, right? So it's one of the probes, but it has a special place. So first, the physics of gravitational lensing is very clean and is purely gravitational. We don't have to make any further assumptions on general relativity. And in fact, we'll see that it came quite early in the development of Einstein's theory of general relativity. The gravitational lensing played an important role in its history, as we'll discuss in a minute. We can directly probe the mass in the universe, as I was just saying. Since the mass is dominated by dark matter, we can directly probe the distribution of dark matter, and we don't have to make any assumption about the relationship between visible matter and mass. We can directly probe the mass, which is important because our ab initio theories of structure formation, as Anjan will describe, give us predictions for the distribution of mass. But when you want to make prediction about the distribution of visible matter, then it's much more complicated because you have to take into account the very complicated astrophysical processes, such as the collapse of baryons, the formation of stars, the formation of supermassive black holes, and so on and so on. As we'll see a little bit later, not only is it a very powerful probe of dark matter because of this, it also has a very strong statistical power for dark energy. Okay, it's not immediately obvious when you first encounter it, but it turns out that it has, and we'll discuss this. The reason is what we just discussed, is that it's a very strong probe of structure formation, even in a nonlinear regime. And as a result, through the effect of dark energy on the formation of structures, then we can get some very strong information about dark energy. So it is a special probe of the dark universe, both dark matter and dark energy. It's also sensitive to initial conditions, so it can also give us some information about inflation. And because it's purely gravitational, it also obviously gives us a probe of gravity. Okay, so it can address all the four and several other fundamental questions that we have in cosmology today.
So
Yep.
it can't prove baryons.
Hmm?
It can't prove baryons.
Well, I mean, baryons contribute to the total mass budget. So baryons also follow the dark matter during structure formation. So it is influenced by baryons. So in fact, as we'll see later, actually, baryons is a correction which is non-trivial that needs to be taken into account. But the idea is that we want to try and probe the dark matter, which we can't see. But baryons are also are not negligible. I would say almost unfortunately for the measurements, at least on some scales. On large scales, the baryons are mostly negligible, but they affect on small, because they follow the dark matter quite well, but on small scales, one needs to take that into account. I mean, it's sensitive to mass, so whatever is a mass fluctuation, whether it's baryon or dark matter, would have a gravitational lensing effect. It turns out that the baryons collapse at the center of overdensities of dark matter, and towards the center there's a peak in the density from the baryons, an enhanced peak, and that's an effect that needs to be taken into account in some of the lensing measurement. We'll discuss more of that a bit later. Now, another motivation for studying gravitational lensing is what I was saying later. This is an area which is seeing very rapid progress right now, and that's because new instruments are coming online. In particular, wide field instrument in the visible and near infrared. So as we'll see, in order to make weak lensing measurement, one needs very large parts of the sky and very deep observations, so very high sensitivity. That means we need very large cameras on very large telescopes. And the next generation of experiments for wide field cameras on wide field telescopes are just coming online. In particular, the Dark Energy Survey, PanSTAR to some degree, the VST, and Subaru are now in the process of giving out their first data sets, and will review the current state of observations and the latest results from these experiments, and then their future experiments like LSST, Euclid, WFIRST, that are also being planned with even more, which will give us even more precision on these measurements. And some of the experiments are in space, some of these experiments are on the ground, and there's also some very interesting technological issues that we can also discuss. As I said, also in the radio, one can also, so gravitational lensing is independent of wavelengths, so it's completely achromatic. So it bends because it simply proceeds from the curvature of space-time. A photon will be the trajectory of photons will be affected regardless of its energy or its wavelengths. So in principle, we can measure gravitational lensing in all wavelengths. In fact, it's been done in several wavelengths, and there's some very interesting prospects in the radio for making weak lensing measurements. It's already been done once, and there's now effort to try to do this even more precisely. So again, not only has a special place in cosmology because of its special gravitational nature, but also there's a lot of observational data that is coming now and that continue to come in the next decade or so. So it's a very exciting time to study and make lensing measurements. Okay, so what will we discuss? So after this introduction, which I just finished, first I'll describe the principles of weak lensing well, I will state the fundamental equation, which is the lensing equation, and then we'll see how everything derives from it. Then I will give you a sketch of the derivation of the lensing equation using a general relativistic derivation. I won't derive it fully, but I will give you a sketch. Then, before moving to weak lensing, which will be the most part of the course, I'll spend a little bit of time on strong lensing because it's related, and also there's some interesting aspect and sort of demonstration of the principle of weak lensing. And then I'll talk about weak lensing proper. I'll talk to you about the different statistical tools that we use for weak lensing. I'll tell you how we make the measurements of weak lensing, tell you some of the theory of weak lensing, the current statistical observational status, and the future prospects that we can hope to have. Next, but where the relative position of the lens and the source and the observer matter. Okay? If you make the lens too close to the observer or too close to the lens, the lensing effect is still there, but it becomes very small. So there's an efficiency factor that basically give us optimal geometries for the lensing effect. Okay, so let's start with the principles of gravitational lensing, in general, and then in the process we'll introduce the notion of weak lensing and strong lensing. And I think a nice way to do this is to start with a historical introduction. And basically, gravitational lensing was very intimately linked to the development of general relativity. And in fact, discussion of gravitational lensing came about very early on in the history of the development of Einstein's theory of general relativity, which, as I said yesterday, was celebrated, was developed in 1915, and we celebrated the 100th anniversary of general relativity last year. Okay? So in 1915, Einstein wrote down this equation of general relativity, and then, which is a beautiful theory. I think many of them have taken the course. If not, I really encourage you to do this. I think it's one of the topics in physics which I think make you love physics. I mean, it's just extraordinary theory that with such simple principles one can explain a phenomena of gravity and also completely change the way one looks at the gravitational processes. So soon after the equations were written down, there was a number of consequences of the theory or application of the theory that were calculated, and one of them is this what we now call gravitational lensing. And the situation, the generic situation, is the following. I think I have a is the following. So that's a generic lensing situation. All right. So we have the observer on Earth. Okay. We have a source, could be a star in this case, and then we have a lens, which is in case is the sun. All right. And so what Einstein calculated is what would be the trajectory of photons traveling from a star all the way to us if it goes past in the vicinity of the sun. A very simple calculation. In his new theory, as I said before, in his new theory, there's no action at a distance on the particle by one particle by a mass, let's say the sun. The way to think of gravity is that the sun curves space-time, and the particles are traveling in the straightest possible paths, and the straightest possible paths are curved because the space-time is curved, and therefore they follow curved trajectories. So he computed that, and he also compared that to one would expect from Newtonian calculations, if we assume just Newtonian gravity, the force going like 1 over r squared. Now, of course, in Newtonian gravity, strictly speaking, the photons are not affected by gravity because they are massless, right? So strictly speaking, if we calculate in Newtonian gravity the effect of the presence of the sun on the photon trajectories, we get nothing. However, you can think of it, you can kind of ignore this and compute what happens for a particle of finite mass, and it turns out that then the mass cancels in the equation, and then you can say that photons would be affected, and then ignore the fact that photons are strictly not affected, and still think of what would be the deflection, the effect in this Newtonian gravity, ignoring the fact that photons are massless. All right, and if you do this calculation in Newtonian gravity, you can calculate the deflection angle, which is the angle between the true position of the source, so the true position of the source, so between the straight line connecting the true position of the source to the observer, to its apparent position, which is the apparent position that one observes because of this effect of lensing, right? So the photons get deflected. As a result, the observer sees the source. The source appears to be coming from this position, even though it's actually at this position. Okay, and one can calculate this angle. It's very simple. You can do it. and you get 2gm c squared over b, where b is the impact parameter of the photons. In other words, the shortest distance between the photon trajectory and the center of the sun and the sun. Okay. Now Einstein then did the calculation using general relativity, and remarkably he got 2 times this result. So he got 4 gm c squared over b. All right. So of course this is quite puzzling and very interesting, because then one can think, well, perhaps we can try and measure this and see whether we can validate the theory using a measurement. And in fact, that's what was done. Soon after, in 1920, Dyson and collaborators, and also the famous Eddington and also Davidson, did a famous measurement of the deflection angle for a star in the behind in the vicinity of the sun. Well, I mean, on the sky in the vicinity. So they measured the position of a star and saw how it was affected by the sun as the sun moved close to the line of sight between the star and the Earth. And they found indeed the 2 times the Newtonian predicted value, and that validated, or that came a long way to validate Einstein's theory of general relativity, which until then was quite controversial. People were not sure that it was the correct theory of gravity, and after that it gave it a lot of credit. In fact, it's the experiment that also, it got quite a lot of media attention, and this is the experiment that also made Einstein famous to the general public. So after that, Einstein became also a celebrity. Okay. And then after this, so by the way, they used an eclipse because at the time they didn't have all the technology to mask the star. So of course, in order to measure the position of the star, one needs, the star is much less bright than the sun, obviously, so you have to occult the sun, because the light contrast between the sun and the star is very high, so they use the natural eclipse in order to facilitate the measurement. And then after this, there was a more theoretical work, and eventually the use of this technique to probe other lenses other than the sun and apply it to various cases of astrophysical interest was done in the 40s, and Franz Zwicky in particular was one of the physicists that did a lot of these early developments of gravitational lensing. All right, so let's look at this more precisely. But the equation that govern gravitational lensing, but basically the fundamental quantity is the deflection angle, which in the case of a point mass here, the size of the sun is irrelevant, is given by this. This is the entire physics of gravitational lensing is basically this. Very simple, as you can see. And in fact, in lensing, it's one of the nice area of astrophysics where most of the principles and the physics of gravitational lensing is encapsulated in a single equation, and everything is derived from that single equation. So again, the physics is clean. And this is basically the equation, which we'll walk through step by step, because this is the foundation equation. Okay, so let's look at the lensing geometry a little bit more precisely. So we spend a bit of time on this slide. It's very busy, but let's walk through it step by step. So let's look at the lensing situation in more detail. So let's O be the observer, S is the source. So in the previous case, it was a star. And the lens here in this is called D. In this I call it L because now we use L rather than D. The D like deflector, now it's more usual to call lens. So sorry, it's slightly inconsistent in the figure and the equations, but I think you can make the jump. So this is the source here, the observer. Now let's define the number of distances and angles. So there are different important distances. So first, that's the distance from the observer to the source. So let's call that ds. Then there's the distance from the observer to the lens. Let's call that dd or dl. And then there's the distance from the lens to the source, which we call ds or dls. Okay, so these are the 3 distances. And then there are angles, right? So there's the intrinsic position of the source if there was no lensing. So that would be compared to the line of sight. We call it beta. All right, so that's the angle that the source would appear to be at if there was no lensing. Then there's the image of the apparent position of the source, which is here because of the deflection of the photon. So this is the photon path, okay, in this simplified diagram here. So the source appears to come from here. So the image of the source, because of deflection, is here. So the apparent position of the source on the sky is theta. And then we call the difference between theta and beta, let's call it alpha, okay, which is the deflection angle. All right? And so the lensing equation is very, very simple. It's the first equation. It's basically that theta is equal to alpha plus beta, which is obvious from the diagram. Okay, so it's not very mysterious. Or you can write it as beta is equal to theta minus alpha. Okay? So the position of the source, the true position of the source, is equal to the apparent position minus the deflection angle. All right, so that's extremely simple, and that's called the lensing equation. Now, of course, all the difficulty or the complexity, which is not that great as we'll see in a minute, but it comes into the calculation of the deflection angle, of course. Right? So the deflection angle, in general, depends on the position of the source, but it's more convenient to think of it as a function of the position of the image, it turns out. It's easier to express it that way. And one can show that just from the previous law before, from this deflection angle, so the deflection angle here is in the case of a point mass, but if we want now a general lens which can have a mass distribution with a given density, then the deflection angle is given as follows. All right? So one can show that the deflection angle is given to the following. So it's given to an integral over the sky, okay, over the position, all the possible positions of the image, times this kappa, which, as we'll see in a minute, is a measure of the projected density of the lens. All right, so you take the density of the lens and project it. That gives you a two-dimensional density, a surface density, basically. That's kappa in some units. I'll talk about this in a minute. Times the kernel, which is given by this, theta minus theta prime. Theta prime is the variable of integration over theta minus theta prime squared. Okay. So if we want to calculate the deflection angle, we obviously need to know the density the density of the lens and the density distribution of the lens. Once we know this, then we integrate with this kernel and we get the deflection angle. All right. Okay, fine.
That alpha hat.
Yes.
Same as that alpha?
Yeah, so this is actually this alpha here.
Yes.
Yeah. And this is alpha hat, which is over here, which is the one we had before. Yeah. So for the moment I'm talking about this alpha here. That's a good point. I'm talking about this alpha. Yeah. Yeah.
Why do we have vectors?
Because, okay, so here we're showing that everything is a line. So we have the line of sight here, okay, and here we're looking at all these lines and this position are aligned with the blackboard, which is one of the planes. But you can imagine that the source can be also on the sky at a different angle. So this position of the source is actually two-dimensional on the sky, okay. And what we do is we consider two planes. We consider the source plane, which is the position of the source in two-dimensional on the sky, and then the image plane, which is the position of the image also on the sky. And this can be thought of a mapping between the two-dimensional source plane and the two-dimensional image plane. That's why we have vectors. It's hard to draw, so here we draw it only in 2 dimensions, but it's really 3-dimensional. Okay. So then what is this kappa? So this kappa is called the convergence, okay?